Chapter 4 is all about where acceleration comes from. What is the cause that matches acceleration's effect? And we turn, as we will continue to do from now throughout the course, to Isaac Newton, Sir Isaac Newton, excuse me. But the interesting thing about it is that we already sort of have an intuition for how this works. If I push on a thing, it moves. If I push more, it moves more, generally. So I might say that push is proportional to motion. If I push on two things equally hard, equally much, and one of them, well, if one of them moves more than the other, I say the one that doesn't move as much is heavier, harder to push, in other words, more difficult to push, well, more difficult to move. That's the story. that's Newton's laws. We just want to assign language to them that matches the language we've already developed. When just now, when I was saying move, let's talk about acceleration. I want to change what a thing is doing. Right now, this thing is at rest. I want it to move, so I want it to have a velocity when it didn't before. I want it to accelerate. So when we talk about pushing a thing in order to get it to move, that motion, we're talking about acceleration. When I talk about push, I suppose we could also talk about pulling, like if it's like a rope attached to it or something. A push or a pull. I'd like to call that force. This is my second least favorite definition, or anymore it's tied for first. This is a terrible definition, but it's the definition we have. If I act on some object in an attempt to accelerate it, generally that means I am applying some sort of push or some sort of pull, and the language that we'll use in physics to talk about that is that I apply or exert a force on that object. So earlier, just a minute ago, when I said that if I push on a thing more, I push harder, if I use a greater push to the same object, generally, we observe more motion. Well, that's like saying force, which, let's use a capital F to talk about force, is proportional to acceleration. The more push, proportionally, the more motion. And that other thing I said is that if I apply a force, an equal push to two objects, and one of them moves more, the one that moves less in colloquial language is heavier. It's harder to move. It's harder to push. It's harder to get to accelerate. How do we quantify harder to move? You guys remember Bill Nye, the Science Guy? one of the best theme songs of all time. If you YouTube, maybe I was gonna play it over the lecture, but maybe I'll just let you link to it. If you actually listen to the Bill Nye the Science Guy introductory theme song, there's a voiceover at one point that says inertia is a property of matter. Inertia is a property of matter. If there exists matter, then there exists some amount of inertia. That's what that voiceover claims. Now, matter, in other words, how much matter exists, that's material extent. That's mass. That's what we said mass was going to try to talk about. Mass was our measurement of how much matter is here. And if inertia is a property of matter, then asking how much inertia is like asking how much mass. Mass is doing the job for us of quantifying inertia. So what is inertia? Inertia is the tendency of matter to resist changes in its motion. The more mass a thing has, the more that thing tends to resist its motion velocity being changed. In other words, the more mass a thing has, the heavier it is in our colloquial language, and the harder we have to push it to get it to accelerate. Inertia. Mass. So another way to, okay, so for a given acceleration, as we increase the mass of the thing, the more mass a thing has, the harder we have to push to get it to move. The more mass a thing has, the more inertia it has, the stronger it tries to resist changes in its motion, the harder we have to push. Put these two ideas together. Force is proportional both to mass and acceleration. And if you're Isaac Newton, you say, you know what? Why bother with a proportionality constant? I'm writing this law as I go. Let's just say the proportionality constant is 1 and that the force exerted is expressible as the product of mass and acceleration. Or that if I apply a force to some mass, I get some acceleration as a result. This is a better way to put it, but this is how we usually write it. Force equals mass times acceleration. Newton's second law. And we are going to come back and back and back to Newton's second law. We are not going to get away from it. It is in many ways the story of the rest of the course. All right. Gravity is a pull. It's some sort of cause that creates the effect of acceleration. If I drop a thing, release a thing from rest, it falls. And we call the cause that creates that effect gravity. So gravity is a force. It's the force that pulls us down when we fall. Okay, cool. Later in another chapter, we'll talk about we'll talk about how to quantify gravity and how to figure out how strong it is. The What's enough for us to know for now is that it's the Earth. The Earth's mass does a thing and exerts gravity on other masses in its vicinity, pulls them towards it. So that's happening all the time, regardless. So these markers sitting here on the whiteboard tray, is gravity acting on the marker right now? And I could let go and it would fall. But what if I'm still holding it? Is gravity still acting? If I pick up a heavy thing and just hold it here, that requires effort. And it requires effort because gravity continues to act. And I need to act to counteract the effect that gravity would have of causing that thing to fall. All right, so gravity is acting on the markers. There is a force. They have mass, but they are at rest. They are at rest because they're on the whiteboard tray. And if the Earth's gravity continues to act, then I'm forced to conclude, I must conclude that there is another force other than gravity also acting on the markers. Otherwise, they would accelerate. An object acted on by only gravity is in free fall, accelerating at 9.8 meters per second squared. These markers are not doing that, which means there must be some additional force acting. In order for the acceleration to be zero, as we observe, we must need to talk about not only whether there is force, but what all the forces are. And we indicate that with a summation operator. This weird looking capital E thing, it's a capital sigma. It's a Greek letter, and it's very like our delta. Delta V means change in V. Sigma F means add up all the F. Add up all the force that's acting on the mass M. That is related to the acceleration of that mass, of the object with that much mass. Now, acceleration is a vector. That's how we defined it. An acceleration, a vector times a scalar is still a vector. And if this equal sign is to really be a thing, the left-hand side needs to also be a vector. Which means this sum, the add up all of the vector forces, means that we have to add these like vectors. We cannot just add 10 and 20 and always get 30. Sometimes the answer is 10, because 10 this way and 20 this way adds to 10 altogether. So we have to add these like vectors according to their directions and their components, and we add them like we have added all the other vectors we've tried to add. We can use components or tip to tail if we draw it. This equation that we've written here is Newton's second law. It's called Newton's second law, and I don't know. I mean, I think the numbering is kind of arbitrary. It's called the second law because in order for this to be a reasonable thing to claim, Newton first had to convince his audience back in 1604 or whenever it was he was writing of the truth of his first law. And it was a big deal because it contradicted a lot of what was thought at the time, in sort of the tradition of Aristotle, that the natural state of things is at rest. And we could be forgiven for thinking that I look around and everything I can see right now from here, I look out the window, everything in this room, if I relax and just look around, everything I can see is at rest. And if I roll a ball, yes, it stops. It makes me think that the natural state of things is to be at rest. And that was Aristotelian thinking for a long time, really until Isaac Newton. And Isaac Newton proposed what is essentially a special case of this law. What if it is true that there are no forces, or at least that the vector sum of all the forces acting is zero? What if nothing is acting on an object? And his answer was, well, that means that the acceleration of that object is zero. If it is moving, if it has velocity, its acceleration will be zero and its velocity will stay what it is. Objects in motion and objects at rest remain so. This is two different phrases. Objects in motion remain that way. Objects at rest remain that way. Unless acted on by net, add them all up, external force. That's Newton's first law. And we number them that way. I mean, you could think about that as just like a corollary, a special case of the second law. If the left-hand side is zero, the right-hand side must be zero. That's what we just said. Remain, acceleration zero. But it's noteworthy to put that first because it means that the natural state of a moving object is to continue moving, to not change its state of motion, which is a little bit hard to wrap your mind around if your entire experience is terrestrial. Moving things generally slow down and stop. The things that don't, well, the motion of the sun from one side of the sky, horizon, to the other, does not appear to stop. The motion of the moon. Well, now that, so Newton has his telescope and he's looking at the motion of celestial bodies as well as terrestrial ones and saying, well, if those ones stay moving, what does that mean about, the effects bodies have on each other? It must be those interactions that change the motion, and that if nobody touches the thing, it's just going to keep doing what it's doing. That's the first law, and it was a big deal at the time. So yeah, I guess it makes sense to call it the first. If that's true, okay, fine. How do we get a thing to move? How do we get an object's motion to change? By exerting a net external force in this calculation, in this proportionality. According to the mass that we have to use so and so much force. External force, because An object can't really exert a force on itself, and we just want to make that clear. I can't lift myself by pulling on my own shirt. External force. This word external is going to be increasingly relevant in a couple chapters when we talk about momentum. So just keep that in mind. First, second law. The third law Newton's third law is the one that has been sort of colloquialized by, I don't know, the greeting card industry in Hollywood and whatnot. If I start it, you can finish it. Every action has, and you finish, and you say an equal and opposite reaction. And I guess that's true, or isn't. I mean, it's a nice thing to put in a, on the inside of a chocolate wrapper, but how true is it really? Sorry, had to hydrate. If one object exerts a force on another, if I exert a force on the wall, let's see. I just hit the wall over here. If I exert a force on the wall, then the wall exerts a force on my hand, and that's why my hand is, tingling a little bit. I can feel the result of that impact. If I walk around all day or stand, by the end of the day, my feet hurt because every time I put my foot down, I'm applying a force to the ground. The ground is applying a force back on my foot. Every time I take a step, the ground steps on me exactly as much as I step on the ground. But it's not just that every action has an equal and opposite reaction. It's that if an object 1, let's say, acts on object 2, then exerts a force on, acts on object 2, then object 2 acts equal and opposite. Now, I'm using shorthand here. E and O, equal and opposite. Acts with an equal and opposite force on object 1. The action-reaction pair is, two things need to be true about it. 2 objects need to be involved. The interaction is mutual. One on the other back on the one. The 2 forces in an action-reaction pair act on different objects. The eraser here held up, gravity acts on the eraser, pulling it down. The Earth's gravity acts on the eraser. It doesn't accelerate because there's a force from the whiteboard tray, but that's not the reaction. If the Earth's gravity acts on the eraser, then the eraser acts with an equal and opposite force on the Earth. If the whiteboard tray exerts a force on the eraser to hold it up, then the eraser exerts an equal force back on the whiteboard tray, which explains what happens when I put a thing on this whiteboard tray that is too heavy. Why does the tray break? And it's because that heavy thing was exerting a force on the tray while the tray was trying to hold it up. That's Newton's third law. And Newton's third law is the fact that forces two objects exert on each other are equal and opposite. That helps us when we talk about forces that are external to things later when we talk about momentum. So we'll come back to this law as well. There's only a couple other things in chapter 4. In chapter 4, we define what we mean when we talk about weight. What is the weight of a thing? And the answer is that it's the mass times the acceleration due to gravity. We never multiplied by the mass before. We were talking about, lowercase g, and we never multiplied by the mass. mg. But mass times acceleration should be force. So the weight of an object is the force of gravity. So we can write W equals mg if we like. All right. This is fine. Trying to think if there's anything else in chapter 4 that we need to talk about, and I don't think there is. Chapter 4 goes really quick. So let's move on to chapter 5. One more segment this week.